Good morning. Good morning, Adriana. Good morning, Tyler. Good morning, Luis. Good morning, Zoe and Kiera and Ava. Okay, I think we just got about everybody. So it's 10 o'clock. So I just have to apologize. It's my fault that Verona schools aren't closed. I jinxed it last night. Within like 10 minutes, Madison Metropolitan Schools closed. Then my children's school closed. Then my son's daycare closed, all within like 15 minutes, like boom, 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 closing, closing, closing. So then I thought, oh, we're going to close for sure. Because they never closed the night before. And so that's when I was like, oh, I better prepare my lesson plans, because they told us that if we close, they even sent us an email. If we close, you need to make sure that you've got lessons uploaded for students to do tomorrow. So I was all set to go for a school cancellation, and it didn't happen. So it's my fault. I jinxed it. All right. Any questions before we jump into the objectives for today? All right. I'm going to switch over to the iPad. All right. So today we're going to talk about reaction mechanisms. You read about them in the book yesterday. And a reaction mechanism is a series of steps a reaction goes through. So, oh, I gotta let somebody in. When we look at a reaction like this, nitrogen dioxide plus fluorine goes to that strange thing, nitrogen dioxide fluoride. We've taught you how to balance reactions, but what we haven't kind of taught you is that we have this reaction, but we actually don't know how it occurs. I'm just going to pictorially draw this. You don't need to draw this. If here's one NO2, here's another NO2, here's another fluorine, what are the odds that all three of these things are going to hit at the same time and have enough energy to break their bonds and react? Okay. I mean, imagine if Zoe, Ari, and Kiera all had a baseball in their hand and you threw all three of them at each other. What are the odds that all three baseballs would hit at the same time in the same place? Not very high. So when we've been writing reactions, we've been writing basically an overall reaction. The reaction mechanism is the actual steps that occur. And the only way you can discover the actual steps is really by like 10 years of research. I mean, it takes a long time to actually figure out how a reaction occurs. So the first step in this reaction is one nitrogen dioxide collides with a fluorine and forms this and monatomic fluorine. Now we know that fluorine likes to be diatomic, not monatomic. So this fluorine is in a highly energetic state. And when that fluorine bumps into another nitrogen dioxide, it will react to form this. So this reaction mechanism has two steps. So the overall reaction is misleading because at no point do two of these collide with a fluorine. That never happens. One of these collides with that. All right. An intermediate is a product that is formed in one reaction but consumed in another. So when we look at step one, we see that monatomic fluorine is produced. But in the second step, it is consumed, it is used up. So we would say monatomic fluorine is an intermediate. That's opposite of a catalyst. A catalyst is used up in one reaction and is produced by another reaction. Okay. Now, we call these elementary steps. So there are two elementary steps. Any questions so far, or anything I can clarify? So the rate law for elementary steps only Nope, I ran out of space. So for elementary steps, the rate orders are equal to their molar coefficients. So that means M would be 1 and N would be 1. Now it's important that you read the chapter because you cannot just rely on me. I will clarify and help explain things, but it's good to get another explanation from the book. Just like in college, you cannot just rely on your professor. You've got to be the one teaching yourself. For this one, again, what I do here, Ian, is I just write my reactants. And then they get raised to their molar coefficients. Now these are different K values. So that's a different K from that one. So how can I distinguish those Ks? Well, in math class, you use a little tally mark called a prime. So I've got K, I've got K prime. So they're both constants, they're just different values, okay? You cannot use the molar coefficients for the overall reaction. Okay, so I cannot just say, oh, there's a 2 there, so that has to be 2. You have to solve these two for an overall reaction. You have to solve it like we did in the last 2 problem sets. Okay, only for elementary steps can you use the molar coefficients, right? Do you understand that? Only for elementary steps does the molar coefficient give us the rate orders. Now, if you've ever gone hiking, you can only hike as fast as the slowest person in your group, right? If there are 4 of you hiking, 3 of you don't just take off and leave the slowest person behind. Similarly, the reaction can only proceed as the slowest step. So they want to find out which step is slower. Is step 1 slower or is step 2 slower? Whichever one is slower, that is going to be the rate law for the whole reaction. So now what they what they usually do is they just tell you. They say step 2 is fast, step 1 is slow. That's what they usually tell you. They don't give you a number, they just say this one's fast, this one's slow. Since step 1 is the slowest step, then step 1 gives us our rate law. For the reaction. And so that is why you cannot use the molar coefficient to determine the rate order for the overall reaction. So for the overall reaction, it's first order with respect to nitrogen dioxide, and it's first order with respect to the fluorine. Okay. Any questions so far? And this is important because this is always asked on the AP test. There are only 2 variables that change the rate constant, K. And that is temperature and a catalyst. Those 2 things will change the rate constant. So types of elementary steps. There's unimolecular, where just one molecule just decomposes and turns into something new. I'll give you an example of this. Don't write down the example, but hydrogen peroxide, when light hits it, it breaks apart into H2O and monatomic oxygen. So here's an example that it's not reacting with anything else. Light just strikes it and then it breaks apart. Okay. And the reason why I don't you write down this example is because here it has 2 products. That's not always the case. All right. Because I want to stick with my example up on the top, which is just one thing decomposing into another. Since it's an elementary step, I raise it to the first order because there's a 1 there. Bimolecular is the most common type of elementary step where 2 molecules collide. And it could be 2 of the same molecule, like fluorine combining with a fluorine, or it could be 2 different molecules. Just gotta let somebody in. All right, so in this case, it'd be to the second order, right? because I actually have two of them, right? For here, A is to the first power and B is to the first power. We would say overall rate law is to the second order. So the overall rate law, you just add up the individuals. Termolecular is not very common. That means three things colliding at once. And like I said, if three people threw three baseballs, the odds of them throwing all the baseballs and having them all hit at exactly the same time is very, very slim. So you could have three of the same molecule colliding. And again, that is not very likely. Remember when I said the rate order can be any real number? It could even be a fraction, okay, or a decimal. But in reality, it's going to be 0, 1, or 2. You know, theoretically, it could be a 3, but how likely is it to have 3 of the same molecule collide at the same time? Not very good. You could have 2 of the same molecule and 1 different molecule. You could have 3 different molecules. And the overall rate order for all of these is 3. So the overall rate order, you just add up the individual rate orders. Okay. So now we're going to look at a potential energy diagram. Actually, I'll draw that a little bit differently. There. So this question is always on the AP test as well. So you have 2 molecules, A and B. And the reaction is A plus B goes to C plus D. Just because 2 molecules collide does not mean they're going to react, okay? There has to be enough energy for them to collide and for them to react. And not only do they have to have enough energy, they got to collide from the right direction, okay? To me, I always think it's kind of like dating, you know? First of all, you got to bump into the person, right? Some of you heard this story before about how I met my wife. I saw her in church, and there were 4 exits to the church. So I knew she'd be going out one of those 4 exits. So I went in and out 3 times before I accidentally bumped into her. So you first of all got to have a collision. Okay. You can't react if you can't collide. Second of all, you got to have enough energy. If you don't have enough energy, if I just would have walked up to her and said, hello, I really would like to ask you. Okay, not enough energy. All right. And you got to collide from the right direction. If I snuck up behind her and said, hi, my name is, I want to go, okay, that would have freaked her out. All right. You got to approach from the correct direction. So energy, direction, and collision. So A and B collide, and as they collide, their bonds begin to form. And at the very top of our diagram, A and B are just about to react. You know, it's kind of like in the movies when 2 people are leaning in to kiss and you don't know, are they going to kiss? Are they maybe going to kiss? Oh, they aren't going to kiss. You know, you got to like lean in and lean. And then if there's enough energy, boom, they react. Yep, you're getting dating advice. I can't think of it. I don't know. All right. So A and B with the asterisk is what we call an activated complex. It's a highly energetic state, and it's kind of like, who knows what's going to happen? Maybe they're going to fall apart and break up and go back to being A and B. Or maybe they just might turn into C and D. So it's that instant moment where it could go either way. They could react, they could break up. So the activated complex is a highly energetic, unstable state. And so it's there only just for a moment. We call this hill the activation energy. It's the energy required for the reaction to occur. So we say EA. And energy is always measured in joules, right? So EA is the activation energy. And then the difference in the height between the reaction and the products is my delta H. It's the amount of energy given off by the reaction. So you remember how we calculated delta H? It's the products minus reactants. So if my delta H is negative, the reaction is exothermic. So looking at this diagram that I drew here, this is an exothermic reaction. The products are lower in energy than the reactants. I'm going to scroll down. If you need me to scroll back up, just let me know. What about this reaction? Now I've got a big activation energy hill. And there's the difference between the reactants and the products. My delta H is going to be positive. So this is going to be an endothermic. So you should be able to tell by looking at the graph, is it an endothermic or an exothermic reaction?
Could you scroll up just for a quick second?
So you should be able to draw it and label it.
Hey, Strauss.
Yep.
Is the activated complex at the same exact point for endothermic?
Yes, it's right at the top. It's just like that moment. You're not sure, are they going to react or are they not going to react? So let's do an example here. I wrote DeltaH, but the book uses DeltaE. They really should be using DeltaH, but they use DeltaE. So let's see if you could draw this. The change in energy is 60 kilojoules, and the activation energy is 30 kilojoules. So a rough sketch, it doesn't have to be perfect. So my activation energy hill is 30. So I know my hill has to be nope. That can't be right. So if the delta H is positive, you know it's going to be endothermic. So the graph is going to look like this, right? My activation energy hill is going to be 60. This difference would have to be 30. So relatively speaking, this should be half of that, right? What if my delta H was negative? And my activation energy hill was 15. Well, then, you know, if it's negative, it's going to be exothermic. My hill is 15 kilojoules per mole. And then this difference is 30. So you should be able to draw something like that, okay? A catalyst speeds up a reaction by lowering the activation energy. So if you go into chemistry, especially hard chemistry, you're going to be spending a lot of time looking for catalysts, trying to make the reaction work at room temperature. So suppose you've got this reaction. And, you know, you could, I'm going to draw it like this. I could give a really big hill, So the change in energy is not that much in this one. A small change in energy. But I've got a huge activation energy hill. So that means it's going to be very hard for A and B to react because there's just such a big hill for them to climb. A catalyst lowers the activation energy hill. Basically, it makes another path. Okay. In fact, when you take biochemistry and you study the reactions of photosynthesis or the reactions of cellular respiration, to me, they are just absolutely amazing because every single reaction of photosynthesis and cellular respiration has a catalyst to lower the activation energy hill and to speed up the reaction. Otherwise, cellular respiration would take such a long time, it would never generate enough energy to power a cell. And so to me, it's just amazing that nature has already figured out a way to do it. So everybody should take biochemistry. Okay, let's see if we can do another example problem here. Find a good problem here for us to do. All right, was one out of the book. So it's the generation of ozone. So that's step one. Step two. So I'll just let you write those reactions down. There doesn't always have to be a catalyst or an intermediate, but in this one, there is. So an intermediate, like I said, is produced in one reaction and used up in another. So here, nitrogen dioxide is produced in reaction 1. It is used up in reaction 2. So nitrogen dioxide would be considered an intermediate. There is another intermediate. Monatomic oxygen is produced in reaction 2, and it is used up in reaction 3. So we have 2 intermediates. Now, is there a catalyst? Is there something that is being used up in one reaction and being produced in another? Nitrous oxide. It's used up in reaction 1, but we see in reaction 2, it is produced again. Therefore, it can go back and react with more oxygen. So a catalyst doesn't get used up. It can go back and continue the cycle more and more. So the reaction starts by nitrous oxide reacting with oxygen. And the fact that it's produced means it can go back and start the cycle all over again. So nitrous oxide is our catalyst. Now let's write the rate laws for these 3 individual steps. Because they are elementary steps, we can raise them to their powers. Their molar coefficients, I mean. We don't need to write that they're gases. So here's an example of one being raised to the half. Now it's going to be a different rate constant for the second step. And it'll be another completely different rate constant for the third step. So we'd call that K double prime. So the first step is fast. Second step is slow. And the third step is fast. So it may seem kind of strange, but our overall rate law, right? It's the rate law, whatever the slowest step is. It's the concentration of nitrogen dioxide that determines the speed of the reaction. So when you look at the overall reaction, you see oxygen becoming ozone, but the rate law does not have any oxygen in there. So it is possible for your rate law not to contain the substance in the overall reaction. So what questions do you have on that?
What number in the book is that?
What number in the book is that?
Yeah.
It's not, I took it off of page 588. It's really not an example problem. I just picked a reaction mechanism there. So for homework tonight, on page 597, you got numbers 59, 61, 64. Really those three. Yeah. I'll tell you the next few problems, but I don't think you're going to want to do them yet. But if you want to work ahead, 69, 75, 79. Okay. Let's see here. Yep, let's just do those. All right, so if you want to work ahead. All right, so I will remain online so you guys can work on those problems, though these I don't think are going to be as bad. Tomorrow I will have office hours at 9 a.m. I've been alternating office hours between you guys and chemistry. So yesterday I had office hours for AP Chem. Nobody came. Today I had office hours for chemistry. Tomorrow I'm going to just open it up to both Chem and AP Chem. So just be aware that if you come to office hours tomorrow, it's going to be a mixture of chemistry and AP Chem. Okay. When will they be due? They're due tomorrow morning at 9:45 a.m. These three. These are not due. Okay. Any other questions?